Okay, good afternoon, everyone. Thank you very much for joining us into another seminar of the Astronomy Department here at IAG-USP. Today, I'm very glad to present Rodrigo Guedes Lang. Thank you very much, Rodrigo, for accepting our invitation to be here today online and giving your seminar. And I will briefly introduce him. He got his bachelor, master, and PhD degree in physics from the Instituto de Física de São Carlos from USP. And later, he became a postdoc at the Erlangen Center for Astroparticle Physics in Germany. And in the near future, he will start a FAPESP Young Researcher position at the Instituto de Física de São Carlos with a collaboration with the Max Planck Institute for Kernphysics in Germany. So, Rodrigo, whenever you are ready, you can start your presentation.
Yes, I hope you can hear me fine, right?
Yes.
Otherwise, okay. So, good afternoon, everyone. And first of all, I would like to thank the organization for this amazing opportunity to present my work here in the seminar and to apologize for not being able to be there in person. I mean, as Maria just said, I am in Germany, so it would be a bit complicated to present this in person, but still, it's a really great opportunity. So I would actually, before starting the full presentation, like to propose a little game with you. So here I have two pictures of the same object in the sky. And I would like, unfortunately, I'm not there to see the reaction of the audience, but I would like for you to try to guess which image costs more to be taken. And I guess it's pretty easy to say that everyone would guess the right side one. And that should be the case. So the left side I took with my own hobby telescope in the farm of my family. And you can see that I'm not really good in doing astrophotography, while the right side one was taken by the Hubble telescope. And I mean, there is a clear 6 order of magnitudes in the price of these two instruments. So I think it's quite expected that the right side image would be as amazing as it is. Let's do the same now for this image for Saturn. And once more, I would very much expect everyone to say that the right side costs more, and you would be right again. Again, the left one I took with my own telescope, just having fun as a hobby. And the right side one was taken with James Webb. There is now 7 orders of magnitude in price in these two instruments, and you can clearly see the effect of these different costs. But now let's look at this. I don't want to say that my picture, which I already spoiled, that is mine here from the label, looks better, but I would say it starts to be similar. You can see kind of similar structures in all of them. You can see maybe stars and other things that you cannot see on the right side. But then, if you look at costs, I took mine also just as a hobby photography with a normal DSLR camera of $1,000, while the right side was taken with the Hess telescopes, which cost a few tens of millions of dollars. So then it starts to be interesting, the money difference to the difference in, let's say, the quality of the pictures. And even more when we look at the camera. So this is my normal camera, which has 24 megapixels as a normal nice camera, while the main camera in the Hess telescopes, which costs of the order of $1 million, has 0.001 megapixels. Then we look at the final one. This is an image of the Crab Nebula. Again, on the right side, on the left side, you can see the details and not on the right side. Unfortunately, I don't have a picture from myself, but the left one is also just an astrophotography with a hobby telescope of around $1,000, while the right one was taken with the LASO experiment, which cost hundreds of millions of dollars. So then on today's presentation, I want to try to convince you why did we actually build such telescopes and observatories, even though maybe it looks like they have much worse images than a simple personal telescope. And even more, why do we want to keep building more? And once I maybe convince you, then I will try to explain a bit better what me and my group is aiming to contribute into these new telescopes that will be built. Okay, to be fair, I was a bit cheating in the comparison because we're not talking about the same thing here. On the left side, I was always talking about optical pictures. So these are optical photons, which mostly come from thermal radiation, while the last images on the right were GeV to TeV photons. But let's look at thermal radiation. So we know that thermal radiation comes just from the random movements of particles. They end up emitting photons following a Planck distribution, which depends directly on the energy of the source of the environment. Here I show the radiance spectral for 3 non-stars. We have our sun in in blue. We have Betelgeuse, which is a colder star in orange, and then we have Sirius, which is a hotter star in green. We see that they all have their emissions around visible. But how about my GeV to TeV photons? Where are they? I need to zoom out a lot this plot. They would be around here in my red light, and we see that stars similar to our sun clearly are not expected to emit thermal photons of this energy. But maybe it's just a problem of temperature, right? I could go to much more hot environments in the universe. So I could look, for example, at the star or at the surface of a neutron star or core collapse supernova that can reach up to 10 to the 11 kelvins, and still we see that none of them reach the energies that we would expect to see these GeV to TeV photons. And there is one extra layer here. Let's now flip the x-axis. Instead of looking at wavelength, let's now look at energy. So we want to reach the GeV to TeV range here on the right side. But as soon as you reach the MeV range, your photon has more energy than a pair electron-positron, so it can start creating particles, and this particle can create more particles. And then in this range, number of particles is not conserved anymore, and you cannot reach equilibrium. So you, by definition, cannot reach equilibrium to emit thermal radiation. So we anyway don't expect thermal radiation in this energy. So where do these photons come from? Non-thermal radiation. What is this kind of radiation? So those are ordered high energy processes that happen in very extreme sources in the universe. For example, if you have intense magnetic fields, you would have charged particles like electrons and positrons being accelerated to very high energy. These electrons then would also interact with the magnetic field, and they would emit photons, for example, via synchrotron radiation. And then you end up with photons, which you already had there, photons that these electrons just emitted, and these electrons can actually interact with the photons that it just emitted, give more radiation to these photons via inverse Compton, and these photons then can reach energies of the order of GeV to TeV. There is another possible scenario, that is, you have your protons, they are emitted to very high energies. Once they reach these very high energies, they will interact with matter that is present in the sources, and because of pion production, these pions will later decay into TeV gamma rays, and you also end up emitting TeV gamma rays. These processes tend to follow what we call a power law, so it's very different from the Planck distribution, and these power laws drop quickly in energy. But anyway, it's through this radiation that we have a unique window to the most extreme engines of the universe. We now have a direct probe of fundamental and particle physics, because these are the most energetic particles that we have ever seen, and much more energetic than anything we can create on Earth. They can help us tracing magnetic fields, the energy balance, the cosmic ray density. They are the only messenger that we actually get from some high energy phenomena, such as relativistic jets and ultra-high cosmic rays. And anyway, if you want to look for a complete picture of an astrophysical source, ideally you want to gather as much information as possible. So we want to join the thermal radiation that we are getting, for example, in infrared and in the visible light, to everything that you can measure from the non-thermal radiation, so we can put this together. But there is one extra problem there. So let's look at the case for the Sculptor galaxy. So this is a very well-known galaxy. It has an apparent magnitude of 8, which means that it's at the edge of being able to see by the naked eye. If you are in a very dark place with a very well-trained eye, maybe you can see, but it's difficult. But anyway, in the visible range, we expect a flux of the order of 1 million photons per second per meter square, which means that if you take a quick 1-second picture with your eyes, you would see around 28 photons. With a telescope like the one I was using to take my pictures, 40,000 photons. Or if you use the VLT, you should be seeing 300 million photons, which is plenty of photons for you to study this object. But if we now go to the high energy range, we go to these 200 GeV photons, our flux is now not 10 to the power 6, it's 10 to the power minus 9, which means that if you again take this 1 second picture. Doesn't matter if you use your eyes, if you use your telescope, or even if you use the VLT, you don't see any photons. And if you want to get only 1 photon from it, you would need either to use VLT looking at this direction for 44 days, then you have the chance of seeing a photon, or keeping in the current theme of the World Cup, you get the World Cup stadium, you put everyone who is seated there to watch the game. Instead of watching the game, all the people are just looking at the sky for the whole game, for every game of the World Cup, and you still will need 50 full World Cups for maybe one person seeing 1 photon in all these 50 tournaments. So how do we actually get these photons? We need to build very, very, very large telescopes, because the larger the telescope, the more likely you are to see one of these events. But of course, if it wasn't complicated enough, there are extra problems that we see, and one of them is the atmosphere is opaque to gamma rays. We know that visible and radio are kind of amazing for doing astronomy because the atmosphere is transparent for them, but that's not the case for gamma rays. So we can use satellites and detect them outside of the atmosphere, and this is something that is done, for example, with the Fermi-Lab telescope, but a satellite can only be of the order of a few meters square. You cannot build as big as you want telescope. And if you go above tens of GeV, the flux drops strongly, and then these detectors are not large enough, which then means you must rely on the atmosphere. The atmosphere is a problem because, again, it makes such that the gamma rays cannot reach ground and it's then opaque, but it can actually end up being our hero. So once these gamma rays enter the atmosphere, they will interact with nuclei or the magnetic field of nuclei from the air, and they will start a cascade of particles, and particles will create more particles and more particles and more particles, up to hundreds of thousands, sometimes million particles, which then at some point get absorbed, and we end up with an air shower that looks like this. And then there are mainly 2 ways of trying to look at this air shower. First one, we put water tanks in a altitude that actually the secondary particles will still be present. And as soon as any of the secondary particles crosses the tank, if they are charged, they have enough energy to be faster than the speed of light in water. So they will emit Cherenkov photons. These photons are of the order of visible, and they can be detected by photomultipliers. And with that, we can, using all the tanks, build a map of the distribution of the shower. And using many different techniques, we can then estimate what particle initiated the shower, what was the energy, where this particle was coming from. And there's a second technique, which is these particles not only emit Cherenkov light in water, but they actually also travel, or many of them travel, faster than the speed of light in the atmosphere. So they will emit Cherenkov light in the atmosphere. These photons, again, are close to optical light. They travel much deeper in the atmosphere, and you can detect them lower, closer to the ground. And then we use optical telescopes, in the sense that they're telescopes trying to capture these optical photons. And then by the light of these optical photons measured by these telescopes, we can again apply a few techniques to get the particle type, the energy, the direction. But all of this full shower development and absorption happen in a few nanoseconds. So remember that I told you that my camera had 24 megapixels. It has 24 megapixels, but the shortest picture I can take with my camera is 0.1 milliseconds, which is 100,000 nanoseconds. I cannot take picture of 1 or very few nanoseconds, and that's why we need these specialized, super expensive cameras. We actually don't care so much about spatial distribution to this level that we need that many megapixels, because the showers are super stochastic and there's a lot of randomness going into the shower, but they are really quick. So we need to have a very good timing resolution for our cameras. And as I said, the atmosphere is our villain because we cannot detect these particles directly. We need to fully understand our atmosphere, the interaction, how the showers are developed, but they end up being our hero. So let's say I don't have an atmosphere. I put a few detectors and I have gamma rays arriving in my experiment. The gamma rays that actually cross my detector will be detected, and the gamma rays that hit outside of my detector cannot be detected, right? Because they didn't cross my detector. which means here these 3 green gamma rays would be detected, but not these 4 red gamma rays, which gives me an effective area of roughly the size of my detector. But now there is the atmosphere. And once these gamma rays enter the atmosphere, they create a much larger shower of hundreds, like 200 to 300 meters. And if you are within this 300-meter pole of Cherenkov light, you can detect it. So for example, this gamma ray here will now cover a much larger area, and it's now seen by 6 of my detectors, which means that it's now detected, even though if there was no atmosphere, it would not hit the detector. So that means that I have a much larger effective area, and I want to have as big of an effective area as I can, because those are very rare events. Okay, so we have these 2 techniques. How do they compare to each other? If we just look at WCD, so the water Cherenkov telescopes, you gotta catch the secondary particles themselves, and these showers don't go super deep into the atmosphere, so you've got to put your experiments really high. They usually are at 4 to 4.5 kilometers, which means that you cannot go to lower energies, because you would have to go even higher, and you cannot build an experiment in 10 kilometers. There's just no land for that. On the other side, IACTs are seeing these Cherenkov photons, which penetrate much deeper into the atmosphere, so you can put them lower, usually at around 1.5 kilometers, which means that you can go lower in energy, even to a few tens of GeV. On the other side, water tanks are much, much cheaper. It's a water tank, you have water, you put 1 PMT. These telescopes are super complex, extremely expensive, which means that you can build, for the same price, many more tanks than you could telescopes, so you can cover a much larger area with the same budget in WCDs. And the higher the area, the better for high energies. So WCDs can reach hundreds of TeV, which IACTs cannot. Also, there's another advantage. These tanks are fully enclosed, so it doesn't matter if it's sun outside, if it's raining, if there are lights around, you're only going to see particles which actually penetrate the tank, so they have close to 100% duty cycle, while IACTs depend on this very, very faint light emitted on the atmosphere. So if there is sun, you for sure cannot even point your telescope up. If there's rain, if there are clouds, if there are many different situations, you cannot observe. Also, at the same time, the tank will detect particles coming from whatever direction, which means that it's mapping almost the full half of the sky all the time, while the telescopes are actually pointing and they see a small circle of the sky each time, so they cover a much smaller field of view. But then this is compensated by the fact that IACTs are kind of slicing my shower horizontally, because the tanks are put horizontally, so I can only see the lateral profile of the shower, while IACTs are looking up, so they are slicing the shower longitudinally, which tells me the longitudinal profile, and I can understand better how my shower developed and end. So IACTs end up with a much improved energy and direction resolution. So if there is a transient event, which I don't know where it's coming from, WCDs will be able to see, because you don't need by chance to be pointing to there. But if there is a source that you need very detailed information about the morphology and understand where most of the particles are coming from, WCDs will not be able to do it because they don't have resolution. IACTs will be able to. And there are many other cases like these that show us that we shouldn't say WCDs versus IACTs, but plus. We need the synergy, we need both of these experiments, and once they work together, this can be the leading frontier in GeV to PeV astroparticle physics. Okay, so going back to my first question, why did we build such telescope and observatories? Here on the left, I show the current generation of IACTs. There are 3 main ones, with the largest one being HESS, which is also the only one in the south. HESS has 4+1 telescopes, so it uses different telescopes. This is important later, we will go back. And then the current generation of WCDs is formed by HAWK and LASSO, also both in the North Hemisphere. And by using them over the last decades, we have come to huge breakthroughs in astroparticle physics. We have tested different acceleration and extreme scenarios of the universe, such as supernova remnant shells, the galactic center, starburst galaxies, classic novas, and we have shown that all of them can reach the TeV range. But also, we have shown that probably there is a chance of having a pevatron in the center of our galaxy. We have seen gamma rays coming from a blazar, which seems to be the same direction where we see an astrophysical neutrino coming for. We established many limits on the frontiers of physics, like dark matter, Lorentz invariance violation. We have the highest ever energy detected photon was detected by LASSO. We are testing galactic magnetic fields. We're testing background light. It's a huge range of physics breakthroughs that we got with them. I will not focus on any of these breakthroughs, unfortunately. I'm quite sure that many of them have already been presented by people in the IAG for you, and there are plenty of experts there that can tell you more in detail. What I want to talk here is what's next. We had these experiments and what's coming around the corner. For WCD, the next generation that is currently in the ending stage of research and development is SWGO. SWGO will be the first WCD experiment in the Southern Hemisphere, which gives it privileged access to important points of the sky, like the galactic center, like the Fermi bubbles, which would be around here. We see in light blue the region that only SWGO will ever be able to see. It will be built in Pampanabola in Chile, which is 4.7 kilometers high. There is a possibility of using dual layer tanks. I will come back to this. And it's a huge collaboration, hundreds of institutes, 17 countries, 4 different continents. We are currently here, as you can see in the time lapse, in the timeline, we decided the site. We are evaluating the candidate configurations when we are at the stage of finalizing the design and starting construction. On the other side, for IACTs, CTAO is the next generation. It is an array of IACTs in 2 sites, La Palma in the north and Chile in the south. So it will give you almost full sky coverage. It's the first experiment to use 3 different telescope types, or maybe 4 even, as it's shown in this image here in the bottom. It will use 13 telescopes in the north and 51 in the south, in contrast to HESS, which is the largest one right now that uses only 5. It's a huge collaboration with almost 2,000 members, 25 countries. There are a few telescopes taking data. IAG is an important member in some of these first telescopes, which are already being explored. And the next telescopes are expected to be deployed this year and within the next years. So we have these 2, which are the next generation. And what do we want to do with them? Why do we actually want to build this new generation? The list of science topics here is also pretty extensive. I'm doing a very short summary of the main questions we want to look at. For example, the origin of cosmic rays. We can look in gamma measurements like pevatrons, the galactic center. We can measure cosmic ray directly. We can probe these extreme environments such as AGNs, GRBs, the Fermi bubbles. We can find new transient events like GRBs, like nova, or even new transient events that we don't know. We want to expand the frontiers of physics through dark matter, LIV, EBL, primordial black holes, and so on. And there is a very strong synergy with other messengers such as astrophysical neutrinos, gravitational waves. You can read in more details about the science case for both experiments in these 2 white papers. But another very important thing that I want to discuss in this seminar and getting to the third point is the importance of Brazil in this new era. So Brazil already has a large participation in both of this collaboration. There is around 15 institutes which are member of at least one of them. We have crucial leadership roles with the spokesperson of SWGO, with the chair of the collaboration board of CTA, and we have had over the previous years strong funding leading to crucial contributions in several areas. For example, in IAG has been a strong player in SST and in the Astronomia array, and now Professor Elizabeth has a new funding for the future of SWGO. And pulling it to my side, there is a new addition to all of these Brazilian players, which is a Max Planck Tandem Research Group with FAPESP. So the tandem research groups are groups focused on early career scientists that the Max Planck helped building to strengthen the collaboration between the Max Planck Society and Latin America. They are always built in a close collaboration with one or more Max Planck Institute and one or more Latin American research institutions and funding agencies. There are currently 7 of them active in the whole Latin America in all research areas, and 3 of them are soon to be established this year via a special FAPESP Young Researcher call, and 2 of them are on the biology and biological cybernetics area, and one of them is mine in astroparticle physics. And in this one, I will be focused very much in this new generation of experiments, CTA and SWGO, with 3 main approaches. One is a transition of the know-how and science goal of the current generation to the new one by mostly the HES experiment. The second one is a strong focus on the development of the low-level analysis and methods for both IACTs and WCDs. And then the third one, the cherry on top, is a diverse range of high-level scientific topics, especially but not only the origin of cosmic rays and Lorentz invariance violation. So now I will be trying to convince you not why we want these experiments, but how can we actually reach these goals and this amazing new science. And of course, I will be very biased towards what I work on and what I aim to work on. So the first one of them is SWGO. As I said, it will be the first one in the Southern Hemisphere. It has privileged access to the southern skies with important stuff, as we see here, like the center of the galaxy, Fermi bubbles, and so on. It will have improved gamma ray sensitivity for a large range of energy, as we can see from the orange line here. And remember, the sensitivity, the lower the better. So we want the lines to be as low as possible here. And we see that orange dominates all of this energy range. Why? First of all, it will have a significantly larger area than Hawk, almost 100 times. It will have improved reconstruction resolution compared to LASSO, given the few factor of things. And it will have improved gamma hadron separation. There are already several analysis developments for achieving this reconstruction and this gamma hadron separation, such as template-based reconstruction, many different deep learning methods, estimation of how the shower is asymmetric over azimuth. But let's try to take a step back and look into details about the gamma hadron separation, especially given dual layer tanks. So this is one of the possible tank designs for SWGO. It's a tank with 2 layers which are fully disconnected to each other, and it has a PMT in each one of them. They're both filled with water. And once an electromagnetic particle crosses the top layer, it will interact. It will create a cascade of particles. These particles are energetic enough to emit Cherenkov light. This Cherenkov light is detected by the top PMT, and you get a signal there. But also this cascade usually is fully absorbed already within the top tank, the top layer, so nothing reaches the bottom layer, so you don't get anything in the bottom PMT. However, if you have a muon, muons will not start this cascade, and they will just emit photons as they travel through, and this emission is just proportional to how much they travel. So you're going to have the muon traveling through the top chamber, emitting photons. You detect them with the PMT. The muon actually continues and now penetrates the bottom chamber, also emits photons, which will then be measured by the lower PMT. And we can clearly see here that we can use the lower PMT as a muon tagger. Why do we want these muon taggers? Muons are crucial indication of a hadronic shower. So it's extremely rare to have muons in showers initiated by gamma rays, but they are very much present in showers initiated by hadrons. So tagging them can significantly help the gamma hadron separation, which is needed because protons are on order, almost 4 orders of magnitude larger background in our gamma ray analysis. So looking for a gamma ray is actually looking for a needle in the hay. But not only we care about them for gamma rays, they actually open a whole new window for cosmic ray analysis themselves. Because when we look at cosmic rays, they can be different primaries going all the way from proton to iron, but the electromagnetic component of the showers, that is what we would usually measure, has a strong degeneracy. A large mass cosmic ray with low energy has similar electromagnetic energy to a smaller mass cosmic ray with large energy. So this makes it very complicated to have an event-by-event separation. But if you look at the number of muons, we can break this degeneracy. So here I show the true number of muons from the simulation versus the true number of electromagnetic energy. And we see that once we find the correlation between them, a clear separation between different primaries appear. So if we can somehow access these two numbers, we could get a better cosmic ray composition separation. And this is something that I have been developing over the last years, which is a template-based analysis for using dual-layer tanks to do cosmic ray separation. And a template basically is you use your simulations and you build expectations for a specific type of events. So the background, so the colorful points here is the expectations for proton showers with different number of muons. And then the red dots is a shower that I measure and I want to find out how many muons it has. We clearly see that it doesn't agree well here. It doesn't agree super well here. It agrees better here. So that's very likely how many muons I have. But this I'm doing by eye. I actually do a likelihood calculation and scan overall the possible number of muons, and then I get the reconstructed number of muons. Using this number of muons, I can then try to guess if it was what kind of primary cosmic ray it was. And here I show for different true primaries what was reconstructed. The dashed line is when I just use the top layer, and the full line is when I combine the information from the top and the bottom layer. And I want the line of this color to be as close to 1 as possible, because then I'm reconstructing the true value of the identity of the particle. And we see this is in log, pay attention to that. We see that there is a very strong improvement when we actually use the information from the bottom layer, which shows us the importance of having this innovative design for SWGO. Another thing is composition based on isotropy. So cosmic rays are very isotropic, but we already start to see small deviations from an isotropy, which can help tell us the origin from them. And we see here that the dipole measuring the cosmic ray has this weird shift with energy, which we don't know where this is coming from. And there are two main scenarios. This can either be due to magnetic fields or due to things unrelated to magnetic fields, and they will behave differently. If this is based on magnetic fields, and I was able to measure these lines for each individual primary of cosmic rays, they would be split, and then I would strongly understand that that was caused by magnetic field. So if I'm able to separate cosmic rays, I might be able to look at the composition-based anisotropy of cosmic rays, which is a significant missing piece for their origin. Two other important problems in cosmic rays is the muon puzzle. So we see that data from very high to ultra-high cosmic rays disagree in the number of muons expected by the simulation, and we don't understand why. And also, we have hadronic models used in the simulations which are not fully constrained because they depend on extrapolations from LHC, and we have conflicting models which are now our leading systematics in simulations. But I said we can actually count muons, right? Or tag muons. And one thing that we are trying to do is using somehow the information in the individual tanks to build the lateral distribution of muons, and then using what we actually measure in this lateral distribution, you can compare to expectations and help solving the muon puzzle or constraining better the hadronic models. So my plans for SWGO, I currently, or my group's plan, I currently am acting as the leader of the Cosmic Ray Task Force in the SWGO collaboration, and we aim to establish the standard cosmic ray reconstruction pipeline. And by that, we need to finish developing and implementing this event-by-event mass separation. We want to apply this to the first data of SWGO as soon as we have first data. We're also developing machine learning-based methods for estimating number of muons using individual tanks. And all of that will be used to try to improve our understandings of the cosmic ray composition and anisotropy, of the muon puzzle, of hadronic models, which help us see a bigger picture of the origin of cosmic rays. And the second case is, how can we get there to the scientific goals that we want for CTA? As I said before, CTA has two sites, which gives us almost full sky access, and it has 1 order of magnitude improved sensitivity and a much larger energy range, as we can see from this red and gray points here, compared to these 3 lines here, which are the current IACT. So the purple, green, and orange, we see a clear drop, which is an improvement in sensitivity, and we also see that they go lower and much higher in energy. And how can we get there? I mean, more telescopes? Probably, right? I told you CTA will have almost a factor 10 more telescopes. Yes, but not so easy to say that it's just more telescopes. Why? When we look at low energy showers will produce few Cherenkov photons, which means that I need very large telescopes with large collection areas to be able to maybe detect these events, which is represented by this cute CTA Lego here. But also, for low energies, my flux is large, so it's okay if my whole experiment covers a smaller area. So ideally, for low energy, I want to build a few large telescopes, and that should help me. But if I go in the other direction, for high energy showers, they produce way more Cherenkov photons per shower, which means that it's okay if my telescope itself is smaller, because there's a lot of photons to be detected. But the gamma rays themselves have a much smaller flux, which means that I need to cover a much broader area. So for that, ideally, I want to build a lot of small telescopes and place them spread apart. And it's the combination of that is the main strategy used by CTA. Also, CTA will have 3 different types of telescopes: LST with 28 meter diameter, MST with 11.5 meters diameter, and here we see a person in a car for scale, and the relative scale of them is maintained here. So that's LST compared to a small car or to a normal car that looks tiny, and SSTs, which are the small telescopes, which will be, again, many SSTs, 37, intermediate number of MSTs, 9, and a small number of big LSTs, which then will allow us to cover low, intermediate, and high energies. So we need this combination of multiple telescopes, but each of these telescopes has a unique camera, a unique hardware, unique systematics, unique electronics. So how easy and feasible actually is to combine the data from these types? Hard to know if you don't have them, but we can actually look at the HESS case. So as I told earlier, HESS is the largest of the current IACT experiments. It's located in Namibia, and it started with 4 12-meter telescopes, and later on built a much bigger telescope, 28 meters in the center. So it is the first IACT to actually combine telescopes of different sizes, and we have been doing for a while. So let's look at how the analysis looks for HESS. If we just look at the 4 small telescopes, which was the first HESS array, I would usually require an event to be seen by at least 2 telescopes, because then I can reconstruct it better. And this is the effective area that I end up having. And then they thought, okay, we want to go lower in energy. Let's build a much bigger telescope. And then if you use this telescope alone by itself, it can actually reach lower energies because, again, it's larger. It gets more photons. If you have a fainter shower, you're still going to get it. But then if you go to high energies, it covers a smaller area. So it's not helping very much. So we see that mono dominates here. Stereo dominates there. But okay, why don't we combine them? And this is usually done via what's called a hybrid analysis, in which I require 2 telescopes of any of the 5. Could be the 1 big one and 1 small one, 2 small ones, 5 of them, whatever. And we see that I get something in between. I do go lower in energy than stereo, but I cannot go really lower in energy because those showers are so faint that they are only seen by the big telescope, by CT5, and I require 2 telescopes, so it doesn't work. And the problem is that when you do a mono or a stereoscopic reconstruction, those are 2 completely different types of reconstructions, and mixing them can be very, very tricky. So how do I get an analysis that actually helps me use the full potential of my experiment? And this is a question that I and a big team in HESS have been trying to answer over the last 3-4 years, 5 years maybe, because I cannot just sum up mono and stereo, because we have overlapping events. There are events which are stereo, so they appear in two of the small telescopes, but they are also mono at the same time. They also appear in the central telescope. There are hybrids which are stereo, and there's all the combinations, and you cannot count events twice, otherwise your analysis would not make sense. What we need is to somehow have a definition of events which are not overlapping, so then you can see them individually and sum them up. But also this needs to happen before reconstruction, because as I said, monoscopic and stereoscopic reconstruction are differently. So we developed the so-called event types-based analysis, in which we have different types. This was supposed to be an M, B, and A, which each one of them will dominate in a different energy range, and they are non-overlapping in such a way that I can just combine them together. And now I finally end up with one analysis that cover or exploit the whole potential of Hess. I mean, that's not the only thing we have been doing. We actually also investigated many other further improvements and further stability of these improvements to data. I will quickly just list them here. We defined new variables which are more complex than the Hillas variables and can give us more information of the gradient over the image. We developed a neural network for determining the image flip, which is basically the direction between the image and the actual source. We have improved in many ways the BDT separation for Gamma Hadron. We have developed a method for cleaning the image, which means getting rid of electronic noise using not only the charge measured by the PMTs, but also the time measured by the PMTs. And when we put all of this together, we actually managed to arrive in the first ever analysis of IACTs applied to data, working on data, which systematically combine different telescope sizes and types. And then here I show the sensitivity for event types, which is the purple, against mono and stereo, and the improvement. And we see that we finally have one single analysis that can exploit the full experiment potential. And also event types plus everything that we did, you can compare the improvement here to that what would be the equivalent observation time increase to get the same improvement in sensitivity. And we get something like 50 to 70, at some points even 100% improvement, equivalent improvement in observation time to what we got there. There are other things we're doing. They're still not into the main pipeline yet, but we have been investigating a shift from the usual frequentist approach that is used for Gamma Hadron separation to a Bayesian approach. We have been investigating the effects of magnetic fields at very low energies. When you actually manage to get to very low energies, magnetic fields like Earth magnetic field plays a big role, and we're trying to model this. But the plan for CTAO from my group in the low-level analysis is the following. So I currently am acting as the chair of the Hess Analysis Package Working Group, and I have been, over the last few years, leading the Hess team that developed and applied to data for the first time an analysis that uses multiple telescope sizes and type. And I think there are two main lessons learned here. Analysis developments can lead to improvements which are as good as basically building a second experiment next to it, which one costs 100 million euros, the other one not so much. But also all of these improvements, making sure that they are robust and work when you apply to data and not just in the simulation world, can be very tricky. So the idea from myself and from my group is to then transfer this know-how into CTAO. There are already efforts in CTAO to develop and apply many methods similar to these or even new methods, but we aim to join these efforts and be part of this team to contribute, bringing the know-how that we learned in the last years within Hess. And I mean, I already started doing some of these. I'm currently part of the team which is working to establish the analysis pipeline for the verification of the very first telescopes that will be placed in CTA South. So once we have the first one or two telescopes, we are far from the final array, but we want to make sure they are working. And this needs a dedicated analysis, and we are currently developing that. And of course, I wanted in the seminar to emphasize a lot how to get to the final science goals and the importance of actually spending a lot of time in developing this analysis and what is being done there, but we have a final goal. We're not just developing gamma hadron separation because it's nice to separate gammas from hadron. We have a final scientific point that we want to get to. And now quickly to close my seminar, list a few of the scientific topics that I am interested in CTAO. One of them is cosmic rays. So cosmic rays are the most energetic particles we know in the universe. You might get a few of them with macroscopic energy. So you have one single protons with energy of 10 joule. But still, they are charged particles, which means that they get scattered around everywhere by magnetic fields. And once they arrive on Earth, they don't point back to their sources. So it's been over 100 years that we detected cosmic rays, and we don't fully understand where they're coming from. And this is one of the main hot topics that we have in astroparticle physics. So CTAO can contribute, first of all, with direct measurements. So, for example, HESS is soon to publish the first proton measurements. I'm not giving spoilers here, but you're going to see it soon. And I am raising the possibility of applying this Bayesian analysis that we're developing for gamma rays to be applied in protons. And then again, the idea is to apply this first in HESS, see how this works in real data, and then transfer all the knowledge to CTA that will have a much better sensitivity and will be able to see better data. But CTA can also study cosmic rays with gamma ray measurements, because the promising sources of ultra-high cosmic rays also would have signatures in the TeV gamma rays. For example, Centaurus A is one of the most promising, if not the main promising candidate source for ultra-high cosmic rays, but we also know it's a TeV gamma ray. It's located in the south, which means that CTA will be perfect for observing it, and we aim to study this relation between TeV gamma rays from Centaurus A and cosmic rays. Also, another thing is the relation between the emissivity of cosmic rays and gamma rays is something that is not fully understood, and it's something that usually enters as an important input for the cosmic ray anisotropy studies. We have 2 years ago shown that you need to take into account a different, in a different way, the Doppler effect in AGNs, and I think there is a lot more to be investigated in this, so we can actually do this mapping of emissivity measured by CTA and expected emissivity seen, for example, by Eugene. And the final one is Lorentz invariance violation. So there are many beyond standard models and unification theories which either predict or they accommodate some level of Lorentz invariance violation, but these effects are expected to be suppressed up to the very high energies. And I mean, astroparticle are the most energetic events that we know in the universe, so they are our most natural probe of LIV. And we can estimate many effects that could be seen in data in gamma rays and cosmic rays. We do that. And what I want to do is to have a complete analysis for gamma ray LIV and then apply to the data taken with CTA, which has unprecedented sensitivity. And by complete analysis here, I mean, usually we investigate one possible LIV effect, but if there is LIV, every effect will be present. So ideally, we want to understand the effects in the source emission, and I have been studying over the last years how this changes the spectrum of inverse Compton emission. We want to study gamma ray propagation. This is pretty well studied in IACTs, and I have also developed a few methods on how to combine different sources for that. And also the final step, which is once this gamma ray arrive on Earth, an air shower is developed, and I have been lately working with other collaborators on estimating the effects in the development of air showers. So putting all of this together, I want to make clear that the field of GeV to PeV astroparticle physics will be led by this amazing synergy between CTAO and SWGO. And you can be excited because there are many discoveries just around the corner. We wait a few years and we will learn a lot about the universe from that. And maybe the main message that I wanted to leave in the seminar is that to get there, we actually need a very holistic, complete approach to these new generations, which is we want to get to the final scientific goals, and this is very important, but we can only get there if we actually understand and spend a lot of time and energy developing the low-level developments, the analysis methods, and everything that goes all the way until you get the final scientific result. And I'm quite sure that Brazil can play a major role in this new area. It has already been playing over the last years, and right now it shows itself as one of the main countries for the future of GeV to PeV astroparticle physics. And on top of that, I'm happy to join the Brazilian efforts. I mean, now on the Brazilian side, of course, I was joining the efforts somewhat in the German side with the establishment of this new talent research group in IFSC via FAPESP. And that's it. If you want to know more, please feel free to write me an email, or of course, we're going to have questions here, but later on, I would also be very happy to talk more about the topic. Thank you.
Okay, thank you, Rodrigo, for this wonderful talk. I will give you some seconds to drink your water while I grab another microphone.
Thank you.
So, questions. Start here.
Oi, Rodrigo. Here is Elizabeth talking. Very nice talk, excellent, very nice overview, very didactic. Thanks a lot. And of course, I have several questions, but let me start with the 2 comments, right? And the comments are with regard to SWGO, that just to clarify, as you know, that this support that we got from FAPESP to develop this project is also a joint collaboration with Max Planck in the same program that you got your grant, right?
Yes.
So of course we are very much interested in starting or keeping this joint collaboration with you guys as well. So you know this collaboration here will be most welcome once you are back in Brazil, but I know that you will be between the two. I mean, both in Germany and in São Carlos as well, right? So this this collaboration will be very welcome. And actually, this project that we are developing for the SWGO is for double layer water Cherenkov tanks, as you might know as well, right? Because this is being developed here in Brazil with CBPF and this company from Rio Grande do Sul, and we are in charge of doing all the analysis of this prototype, the double layer water Cherenkov tank here in IAG, within the framework of this collaboration, right? This joint collaboration. So, of course, all your expertise on these analysis will be also very welcome, right? So I have a question, because you proposed this, this pipeline for improving with regard to the CTAO, right? For improving the data that you have been developing with HES, and this is amazing because with HES only with the 5 telescopes, one big one and the other 4, with this combination you got so much improvement. So what are the prospects, for instance, for CTAO South? Because we are going to have these 37 small telescopes doing stereo all the time, and then there will be the 2 LSTs in the center and the other 14 MSTs. And of course, this pipeline can be implemented already only with the SSTs and a few MSTs. So this can be done in few years from now, right? Because as you know, those telescopes will start being shipped to Southern Array, right? So can you comment a little bit more on this?
Yes, of course. So thanks for the comments. Thanks for the question. So before the question on your comments, as I said shortly before the official start of the seminar, it's a bit sad that I was not able to do it in person there, but I for sure want to visit you as soon as I am in Brazil, because I agree with you that there is a lot of possibilities for fruitful collaboration between my new group and IAG. So I'm looking forward for that. And about the questions, so just to be fair, there has been a lot of work already from the CTA community to develop event types, which is this type of analysis. For CTA, they kind of have been in parallel, somewhat developed for HES and for CTA. And this is up to some point already implemented into the main pipelines of CTA. But I think the main point or the main
not
extra...
yet, it will be.
Yes.
I mean, not yet, because you know.
So I think the main thing to be brought this, and where I think I could help a lot, is, as I said, in the simulation world, things work amazingly. I would say that in my 4 years of my postdoc working on this topic, in the first year, I already did the full implementation itself of the method. And in 3 years, I fought to make sure that this works with data, because you start to get a lot of new systematics that you were not expecting when you join telescopes, and a lot new things that you just could not envision, and you only see them once you look at data. And we want to join the teams who are doing that to bring new ideas that we had for HES, but also bring what we've learned that could happen when you apply to data. And yes, the idea is to, as soon as I start, we will start doing stuff in CTA pipe and in the main pipeline, talking together with the CTA pipe team. And as soon as we have telescopes, doesn't matter even if the first telescope, we will try to run the analysis and see what we can get, what happens to data, and from there on already play around with what needs to be corrected to work on data. So when we actually have a lot of telescopes, it should be smooth and well established.
Right. Can I make another question? I have another question, Rodrigo, with regard to the cosmic rays, because, you know, using those facilities to catch the cosmic rays as well, and muons, this is a natural follow-up, right? But I know that in OG, for instance, there are also these water Cherenkov, doing this. So, and probably all these pipelines, these softwares have been inspired from this experience from OG, right? So what would be the advantage of using CTAO and eventually, you know, Astronomia array for getting cosmic rays? Because in Astronomia arrays, we have also plans to catch muons using the volcano, right? But yeah, so can you clarify this point?
Yeah. So I think comparing to OG, there are two different worlds here. When we go for SWGO itself, it's very similar, and actually the cosmic ray team in SWGO has a lot of pre-OG or OG people. I myself did my PhD in OG, so I also have a lot of experience there. There are a few differences, like we have a much higher fill factor than OG has. OG usually seeing events with very few tanks because they are quite spread apart, while SWGO is seeing with a lot of them, which allows us to do this kind of template-based analysis that OG cannot do it, or at least it's harder to do it in OG. So, and also we will have the dual layers, which OG didn't have in the beginning. OG is now going through the upgrade where they actually managing to tag protons, but this is something that it's new in the many 30 years of OG. And then when we go to CTAO, I think they are complementary, because one of them, we are measuring the cosmic rays directly, and measuring cosmic rays directly with WCDs, it's better. You're going to have less uncertainties, less statistical uncertainties. In IACTs, I would say the main gain is when we look at gamma rays and try to connect these gamma ray measurements with cosmic rays. So basically what I was saying here, that we want to look at, for example, Centaurus A in gamma rays and see what we measured in cosmic rays and connect them. But also when we do direct cosmic ray measurements, there is a different energy scale that we need to understand well. We can probably constrain hadronic models in a different way than we can do in SWGO. So this also complements itself. So there are different advantages in each one. But if I had to pinpoint, the main one for CTA is the gamma measurements of things that are related to cosmic rays.
Okay. Thank you, Rodrigo. And we are going to keep in touch. Mm-hmm.
Yes, for sure.
When are you planning to come to Brazil?
Probably September.
Okay. But anyways, we can.
Yes, for sure.
We can talk. Thanks a lot. And thanks
Thank
for
you.
accepting our invitation to give this wonderful talk. Thanks.
Thank you for the invitation. It was a great opportunity.
Okay.
Okay, any more questions, comments? No? Well, I think we are also running out of time here. So thank you very much again, Rodrigo, for your excellent talk. We really hope to having you here in
Yes.
present soon, or meeting you in Germany, who knows? Yeah.
Yeah, there's also the chance.
So, okay, thank you. Thanks
Thank
a
you.
lot,
Thank
and
you
we
again
keep
for
on
the
touch.
opportunity.
Great. Thank you.
Bye-bye. Thank you.
A gente tem café aqui de lado.